Okay, everyone. Nice to see you all. And this talk, I will talk about the leveraging Ko-Fi for innovative HUD systems. Okay, this is my outline. First, I will give the introduction, and the second is the abilities for modeling the windshield. And then I will start with the simplified model and determine optimization variables and the constraints. Next is the optimization result, and I will reverse the system and analyze the visual performance. Okay. Okay, this is the introduction for HUD. Okay, the HUD magnifies the image on a picture generation unit. We call it PGU, and provides a virtual image to the driver by reflecting the windshield or combiner. The PGU can be the LCD, DLP, or micro LED display. The HUD usually consists of two reflectors, at least one of which is a freeform concave mirror designed to correct aberrations induced by the windshield. The eye box is a two-dimensional area. This allows the driver some freedom of head position to view the entire display. We have two kinds of HUD case study. One is the combiner form generated in 2016. Another is the windshield form generated in 2020. Currently, our AE team members are creating the windshield form in the previous slide. It will be an example model library built into the future version Ko-Fi. In this session, I will talk the combiner form, focus on the design strategy and some powerful features in Ko-Fi. Okay, first I will talk about the abilities for modeling the windshield. If we want to model the windshield, we have three features in Ko-Fi. We can use the CAD surface to model a ray traceable windshield. And second is the stack fit utility. We can use it to fit the stack data to a native Ko-Fi surface. And the third is the modeling this directly using the supplied macro, supplied DLL surface, user-defined surface. Okay. And for the Ko-Fi surface in Ko-Fi, we can import CAD file for ray tracing or visualization. CAD surface allow the engineers to utilize the imported windshield to design HUD. And visualization CAD allow the engineers to easily see clearance issues in 3D viewing feature. And it can shorten design cycle. Next is the stack fit utility. There are two modes for usage. One is the create surfaces by fitting data, and another is convert surface type. For example, the CAD surface in the screen you can see here, and this utility has smooth workflow interface. It can import data or select one existing surface and then fit surface, and finally export surface in Ko-Fi. lens data manager. Okay, we will start with the simplified model and build to a solution. There are two directions for HUD design. One is eye to image, and another is image to eye. And eye to image is a familiar direction for most lens designer. We use the eye to image for setup and the design and the image, and use the image to eye model for analysis. And this is the system layout. In this case, we will talk about the combiner. And the combiner is used to replace the real windshield. And the initial setup, we will start from the 6 fields, and we use the Fridge-Zernike surfaces to model the combiner and the 2 mirror. And we also need to use the Y decenters and the aberrations variables. Then we will optimize by the following constraint. For example, we need to control image size and the clearance and the normalization radius. And first, I will talk about the COFI freeform. It is a powerful surface for the design degree of freedom. And the COFI offers some powerful freedom surfaces for the compact refractive system. This is the COFI built-in surface type in COFI. Such as XY polynomial, Zernike polynomial, fringe Zernike polynomial, extended fringe Zernike polynomial, and the Q2D freeform as field. We also have the user defined surface Chebyshev surface type for usage. Okay, the extended fringe Zernike polynomial, Q2D freeform, and the Chebyshev user-defined surface have the off-axis angle, XY offset parameters to control surface departure more freely. Okay, and next we will determine the optimization variables as a constraint, then do the optimization. And for the object distance, we set it for minus 6 kilometers. So it is equal to 0.167 diopters. Okay, this is the virtual image. Okay, and we need to set some variables, include the appreciate curvatures, thicknesses, and the Y decenters and the aberrations. Based on the off-axis configuration, we will use the freeform Fridge-Zernike surfaces with primary and the secondary terms variable. And also we need to let the normalization radius be the variable, because it will be allowed to vary to remain larger than the bundles. So the constraints include the image scale and the clearance constraints and the normalization radius control. And if you want, you can add more constraint in the optimization utility. Okay, for the clearance constraint, we will introduce a supplied function for the COFI. It is a supplied macro function in COFI, and it means this supplied function supplied macro function is JMRCC. This is the syntax for this macro, and we can see this is control for point to line distance. Okay, so this is the distance control. This clearance control can avoid the interference between the ray and the mechanical part. It is very important. And next is the normalization radius factor. We call it NRF. And several confined surface type requires normalization radius, such as Q-type freeform and Zernike surfaces. And it is a factor for the surface maximum aperture. We use NRF constraint with a variable normalization radius to maintain the normalization radius. Okay. And next is the optimization strategy. First, we need to start with all spherical surfaces and 6 fields and optimize for packaging. Then, second, we need to freeze tilt and decenter on selected components as clearances are achieved. And the third is allowed primary Zernike aberration coefficients to be variable and use the weak constraints on display size. And the fourth is allow secondary Zernike aberration coefficients to be variable and then tighter control on display size. Finally, we should add additional fields and optimize it. Okay, in this slide, we can see why we need to add more field. We can see we can use the FMA feature to evaluate this one. Okay, you can see if we use the 6 fields, we will get the average spot size about 0.191 millimeters. And then we add for 11 fields, we will get the average spot size about 0.091 millimeters. If we add more fields, about 15 fields, we will get more small, the smaller average spot size. Okay, next, this is the optimization result, and we will use the performance result. We will introduce some good feature for evaluating the HUD system. Okay, this is the first one. We can use the FIR ABCD macro to evaluate the system first order properties. And we can use the FMA feature to evaluate the Zernike operations, and we can see what operations dominate this HUD system. And we also can evaluate the MTF. This MTF performance, for the MTF performance, we can use two features to do it. One is the MTF feature, and another is the FMA feature. If we use the FMA feature, we can get the whole field, across the whole field for the MTF value. Okay, and the next is the distortion. Okay, we can use the grid distortion feature to analyze the HUD distortion. Okay, then we can use the angle of incidence analysis to see the performance for the telecentricity. Okay, it while not a requirement, we'd prefer telecentric imaging to avoid illumination issues with the display. Okay, if we after the design, okay, we can reverse the system and analyze the visual performance. And Core has a built-in macro. We call it reverse system SEQ. This is designed to reverse an optical prescription in Core. We can launch it, use the macro manager, and then go to the utilities. We can see this macro and launch it to do the reverse. Okay, and with the system flipped, we can easily model and analyze the performance for both eyes. And we want to analyze these performance, such as RNS blur size, convergence disparity, divergence, and field curvature and astigmatism. For analyzing this performance, we need to create two zoom position with 4mm apertures separated by the desired interpupillary distance. And we need to use the true orthogonal model to modeling the system. And then we use the real chip array data to analyze the convergence and the divergence errors. And we also can use the RNS spot macro function to analyze the RNS blur size. And then we can use the XFO and the YFO database item to analyze field curvature and astigmatism. Okay, this slide shows the convergence disparity and the divergence. For horizontal, for the top view, we can see the eyes have the eyes have the ability to converge but not diverge. Okay, and for the vertical view, the side view, we can see the eye angle should be the same, but we need to evaluate the divergence for our two eye. Okay, and this is the convergence disparity calculation in this case study. This is not the only one definition for convergence disparity. If you have a different definition, you can edit your own macros to do it. So we will calculate, use the formula to calculate the focal length with triple ray angle. And we also can use the XFO and the YFO to calculate the focal length for this this triple ray. Okay, and then we can use this tool the two formula to calculate the convergence disparity. Okay, next is the divergence. I think this is very simple for all of you. Okay. Okay. Next, users need to evaluate the performances for stable head position, and so it's very complex, but we can use the CoFi Macro Plus. It can help users do it easily. And so here is the macro we create for analyze all the parameters on the prior slide, and run the macro, and the following combinations can be analyzed. Okay, this is the example output. Okay, finally, I will give the conclusion. In this session, we learned the strategy for HUD design in CoFi, and the CoFi provides powerful features for modeling HUD. We can import CAD file for visualization and the ray tracing, and we have the StackFit utility. It can feed the stack data file or an existing service and put into a lens model. And we also have many freeform services can be used, and the supplied reverse system macro is designed to reverse the lens model. And the CoFi also provides useful constraints and analysis features such as JMRCC, user-defined macro, and the NRF constraint for optimization. We also have the FMA, MTF, and the FIR, ABCD, distortion grid, and the AOI analysis features. And the Macro Plus can realize more optimization and analysis and make your work easily. That's all. Thank you.
Thank you, Paul. So I think our next technical speaker is Felix. Felix, over to you.
Okay. Good morning, everyone. My name is Felix Chen. So in the first session, Paul has already introduced how to design HUD system in CoFi and analyze the image performance. So here in this session, I'd like to introduce how to analyze the straight line control. And we have a HUD utility can help you to create some some effect analysis and visualization analysis in LightTools. So let's see the outlet. So the first part, I will tell you how to combine the CoFi's lens into LightTools, and we create the image and the eyes receiver to run the image simulation in LightTools. And The second part, we have the HUD utility, can help to analyze the something like uniformity, intensity analysis, and the ray footprints. And the third part, I will introduce the straight line analysis, including the straight line from the windshield or combined reflection. We sometimes call the ghost image. And also some light may come from the sunlight directly or mechanical part reflection. So we use the red pair feature to do the straight line control. And the last part, I will introduce our HUD utility tool to create a sound, and then we can modify the sound angle to analyze the maximum radius on the PGU. So you can analyze the thermal part further. Also, we can include the solar effect for the visualization. So let's see the first part. So once you have the core file designed HUD system, you can save the model to be core files file directly. Also, we provide the other option we call the optical system file. Using this file, you don't need to have the core file license in your system, and then you can import a core file model to the LightTools directly. So as you can see in core files lens data manager, it shows every surface information. And in LightTools, we also include a design feature manager. It provides a similar table to show everything. So you can see here is a button, is an update button. So that means when you modify the core file model and save to the core files format or OS file format, LightTools can update this result directly in our LightTools software. And then if you have the HUD system, we need to simulate the visualization. We need the source and the receiver. For the source, usually we simulate two parts. One is scene, the other one is our PGU, like our display. So we use this tool to import an image. Then this tool can help you to create the spatial optimization data for RGB channel. So for the RGB mesh data, it includes the data value from 0 to 255. So we can use this data to create an RGB source. And then use this one for the visualization simulation. So once the RGB source emit the light into your system, and then the light will combine to a color image. So you can use this feature to easily to create the image source. And then we need the ICE receiver for the visualization simulation. So we use the luminance meter to create the receiver to see the visualization result. So in the spatial luminance meter, we include some parameters like working distance, width and height of the luminous mesh, and the aperture radius. Those values can be modified, and you can get the desired field of view. As you can see, if you use the normal ray to trace the ray from the source to your HUD system, and then you want to hit the as receiver's aperture. The aperture is very small, so it's very hard to capture the ray to the receiver. So here we also provide the other option we call the backward simulation. So the ray will come from the receiver and go through the aperture, then go to the HUD system, then try to hit our PGU or our display or our scene source. So using the backward simulation can enhance your simulation speed. So we will use this method to simulate the visualization. The next slide shows an example for the HUD system. We create a PGU to show some information. Here is the turn left hand, this signal. And then we also create a scene image. So you import two picture to image processor to create the image source. And then we create a source into HUD system to run the simulation. And finally, our receiver can see this result. So we can see two pictures here. The first picture, we don't include the ghost reflection from windshield. So the PGU's image is clear. So if we include the ghost reflection, we can see the second image. The image will become burned because there is a maybe first or second ghost image combined on the image. So that is our visualization result. And once you create the system, you can also scan the image motion when the eyes position move. So for simulate this different kinds of precision, we can use the parameter analyzer. So we define the XY position to variable, and this analyzer can help you to move the eyes position automatically, and then simulation and save the data. So as you can see, when the eyes move to these 9 different positions, you can see different image result. Also, you can see different kinds of PGU scenes. Also, you can see some straight line on the visualization image. So that is the first part about the visualization and create the HUD system in LightTools. And the second part, I'd like to introduce how to analyze the uniformity and the intensity in our LightTools using the HUD utility. So here we provide the tool to capture the different positions data. For example, you have a virtual image result, and we define 9 points here, and we use the tool and capture the maxima and minima data in the table. And that means you have the maxima and the minima data, you can calculate the uniformity for the final result about the uniformity. So that's why we use the parametric control to capture the maxima and minima value to calculate the uniformity. So it's very easy to use for the uniformity analysis. And we also can use the NS ray. This ray can emit a ray grid into PGU. So we can see the ray go through the HUD system and hit the PGU's different positions. For generally, if your system is perfect, the result is like the blue dot. It's a rectangle, but the actually image include the distortion. So the distorted rectangle is like the red dot. So this data can help to determine the level of the required image wrap on the PGU. So this feature also in the HUD utility. And the next one is the intensity analysis. It's talk about the binocular effect. In the first section in Ko-Fi, Ko-Fi can do the same thing for the binocular effect simulation. And so for LightTools, how do we analyze this result? Actually, we create a point source located on the PGU for different position, and we create the left eyes and the right eyes on the different location on the eye box. So we can emit the point source rays and go into the system to try to hit the eyes position. So we look at the rays intensity data to calculate its intensity rays direction. So we can use this data to calculate the angle difference. So if the result is convergence, that is acceptable. So if for the horizontal, is the divergence is undesirable. If the divergence for the vertical direction is undesirable as well. So we use this method, and we also include a red path feature to show only the red hit the left and right eyes, like the blue and the yellow light show here. And then we can calculate the angle to know how the horizontal angular difference and the vertical angular difference. And the result will show as a table list result. So that is the HUD system to help you to calculate this result. So you can use this method to do the analyze for the intensity result. And next part is about the ghost and the straight line control. As you know, LightTools is the illumination software, so you can calculate not only sequence rate but also non-sequence rate. So most of the straight line is non-sequence rate, maybe come from the second reflection or the light from the mechanical surface or the edge of the reflector. So here is an introduction about the straight light. It may cause the artifacts of the image and the bright spots. So this result will affect the driver safety. So as I mentioned, the straight line may come from the reflection light from windshield or combiner, or some display light leak directly to the eyes, or sun or sky light hit the HUD part and then go to our eyes. So let's use the red path tool to run what caused the straight line. For the red path feature, we record every path detailed information, like the path detail and the power, the intensity and illumination data. And you can try to show certain red path to check the image result. So image result will update to you when you only choose certain path. So here we show the primary image, and for the first image, and the second image is the primary and include the first ghost result. So you can see that there are two paths here, green one and the red one. And the third picture we showed both primary and the second ghost image. So every path detail are available for each path. So we use this table to show the ray goes through from the source and hit each surface, and then you can know which surface causes the straight light. So the straight light not only can come from the reflection from the windshield, but also some mechanical part or reflector's edge can also cause the straight light. So we use this example to show this result. So some lights, the first one is the primary image. The second one is the light come from the sky, and it hit the edge of the reflector and go to the eyes. And the other one also hit the edge and hit the mirror, go to the eyes. The last one is the display hit the reflector, and the leak ray go to the eyes directly. So using a red path feature can help you to analyze the ghost image and any straight light from our HUD system, and you can control this some surface to reduce the straight light effect. And the last part, I'd like to introduce the sound routing and analysis and solar effects. So in our HUD utility tool, it can help you to create a sound source directly. And in this HUD utility can help you to rotate the sound angle to different position. So the sound will include is spectral distribution, and when the sound rotates to different position, the sound will emit a ray and try to go to your system, include the windshield, reflectors, and finally hit the PGU. So we collect the light on the PGU to see its maximum irradiance data. Just like the slides picture showed this result. So you can know which angle for the sun's position will cause the strong irradiance result. So that's important data can use for the thermal analysis in the PGU system. And the next one is solar effect. We can use the other tool we call the solar source utility. Using this tool, we can not only create a direct sound source, but also we can create a diffuse sound source. So you can choose a location, and we create that location's direct sound and the diffuse sound source. And for this case, we use this utility to create a source, and we place our paper set partially behind the HUD combiner. And then we run the visualization simulation. So finally, you can see the image. It includes the paper's reflection from the combiner and the windshield. That light is come from the direct sound and the diffuse sound. So we can use this feature to analyze the solar effects. So finally, I will give you a brief conclusion. So LightTools can easily to create the HUD system and do the analyze, do analysis for different kinds of HUD analysis. So our HUD system designed from a profile can be imported into LightTools directly. And then we can create the image source for the PGU and the scenes. And we can use the spatial luminance meter with the backward simulation to perform a visualization result. Also, we provide our parameter analyzer to scan different position of the eyes and capture every result for you. Also, LightTools provide a powerful feature for all HUD analysis requirements, like image simulation and uniformity reflecting analysis and intensity analysis. Also, we have the powerful red path feature to help you to analyze the ghost and the straight light, and you can control the straight light to reduce the effect. And also we have the HUD utility help you to create a sound and direct sound, and you can analyze the sound loading. Also, we can create a diffuse sound source as well to see the source effect for the visualization result. So that's all my presentation. Thank you.
So, okay, we are at our end of our session. So I would like to thank Paul and Felix for delivering a very insightful webinar today. I'm very confident it was very helpful for our audience today. I also would like to thank our audience for taking their time out and joining this session. If you have any further queries related to the subject matter or any other requirement, you can always connect with us. Our details are listed on the screen right now. You can reach out to us at any time and we would be happy to address your queries. Please keep an eye on our upcoming events like seminars and webinars. You can follow us on our social media platform for the same. Thank you.